In this video, I will describe the different drawings of organic structures in organic chemistry. The very first one is molecular formula. So when you're given a molecular formula, it should tell you the kinds and number of atoms of each element present in the molecular compound, but it does not tell you how those atoms of the elements are connected. Let's look at an example. You could have a molecule with the formula C6H6. This could be so many things, including a benzene ring. It could be a benzene ring. So benzene could be one of those that has that molecular formula. Another one with a CCH6 could probably be this structure, with a CH2, a CH, with a triple bond, and then a CH, and then a CH2. 1, 2, 3, 4, 5, 6. So that one has 6 carbons and it still has 6 hydrogens. So you see, molecular formula can be misleading. I can give you another one here, maybe that of an alcohol. So let's say you have this molecule right here. You see, it's gonna be C2H6, and then an O. It could be that structure, but at the same time, the same molecule with the C2H6O could be a molecule of this structure. So you see, you could have molecular formula that translate to different connectivity of atoms. Okay, so that is the molecular formula. Only tells you the number of elements in a compound. Let's next discuss about the condensed formula. For the condensed formula, this one will show which elements or group of elements are bonded to which elements, for example, carbons. Let us consider this example to represent condensed formula. Let's assume that you have a CH3, and then you have a CH, and then probably you have another CH, and then you have a CH3 at the end. This is suggesting to you that you have a CH3 bonded to a CH, and it's bonded to a CH, and then it's bonded to a CH3. By the way, the rule is that carbon, when it's neutral, it needs to have 4 bonds around it. This checks out 3 hydrogens and 1 bond. This one has bond, bond, bond to hydrogen, missing a bond. We need a double bond right there. And then this one has bond, bond, single bond. Okay, that's good. 4 bonds around it, 4 bonds around that, 4 bonds around that. Okay, so this right here is the condensed formula because it's mashed up. It's mashed up. Okay, now let's look at another one. Number 2. Let's say that you have a CH3, and then it comes here and says CH2, a bunch of CH2 repeated, let's say 3 times, and then you have a CH3. So in this example, we'll have a CH3 connected to 3 CH2s in that pattern, and then ending up with another CH3. That's what this condensed formula is saying. Okay, so what if we have a CH3, and then we are given a C, and then in parentheses we are given CH3 2, then we are given a CH3. In this one, this is carbon number 1, let's say so, and this is number 2. That CH3 is bonded to carbon 2, and that carbon 2 carries the CH3s in parentheses, and then we continue with our chain CH3, giving you a branched structure. So these are representation of condensed formulas. Now the moment you start showing bonds, you are alluding to describe what we call the Kekule structures. But now we'll have to show all the bonds. So I'll try pick up similar structures to draw the Kekule structures. Of course, this one is almost a complete one, but I've not shown the hydrogen CH bonds. Let's look at the Kekule structures next. For the Kekule structures, these are similar to Lewis drawings, but shared electrons are represented by lines, what we call bonds, also known as aka bonds. So let's look at an example of Kekule structure. So let's assume that this was the formula that was given to us. So you can translate that condensed formula to a partial Kekule, just to make sure that you have 4 bonds on each carbon. That's why I included the double bond to satisfy the octet rule. And then this translated to the Kekule, let's call that 1, 2, 3, and 4. For carbon number 1, it is carrying 3 hydrogens. Carbon number 2 is carrying 1 hydrogen and has a double bond. Carbon number 3 has that hydrogen and it's also bonded to a CH3. So this will be the Kekule structure of this molecule right here. Now let's look at a second one. Let's assume you have a CH3, you have a CH2 repeated 3 times, and then you have a CH3. In this case, I will first of all, to see it, I'll want to draw at least the bond that is connecting the groups. CH2 is repeated 3 times. That's what the parenthesis says. And then I'll translate this. Remember to count the carbons in the longest chain. I'll translate that to open carbon chains. So maybe I have 5 of them. So I'll go. Carbon number 1 has 3 hydrogens. You see them there. Then the second carbon has 2 hydrogens. You see it there. So is the second CH2, which is the 3rd carbon, also the 4th carbon, and so on for the CH3 at the end. So again, this will be the Kekule structure for that. For number 3, let's assume you have this molecule. This time I'm going to include an oxygen. If that's the condensed formula, this suggests to me partial Kekule, that this is my connectivity, and I will have to show the hydrogens on the first CH3, call that a methyl, and then I'll show the oxygen, and then I'll show the last CH3. Now because we have an oxygen here that doesn't show to have a charge, I have to complete the octet state by including its lone pairs. That is the Kekule. Now you realize here we are failing to show the geometry and bond angles. That leads us to the zigzag drawing. So once you know the condensed and you know how to get the Kekule, you should be doing the zigzag, which is the most common way of drawing organic structure, zigzag and 3D drawings. Let's talk about the bond line drawing. So for the bond line drawing, what you're looking at here is translating your Kekule. So let's say this is our Kekule structure of a small molecule you would call propane. Propane. You will learn about it under alkanes. This is showing that they are like 2D structure, but I would really want to show it in a way to preserve hybridization and bond angle staggered conformation. So to draw the bond line zigzag drawing, which are representations of carbons and hydrogens on carbons implied, you will just draw a line. The moment you put a pen down, count it as carbon 1, take it up, that's carbon 2, and that's carbon 3. So this is carbon 1, carbon 2, carbon 3. I don't need to show the hydrogens. The hydrogens are implied. We know they are there. The only time you're implying hydrogens in an organic drawing is when they are on carbon. If they are on any other element other than carbon, you have to show it. So the zigzag drawing will end up just being that. And that tells me that I have 3 carbons. And I should still be having molecular formula C3H8. Okay. Let's do one that has hydrogens on other elements. So like this molecule, which happens to be beer. Okay, so again, connectivity is like that, and I can translate this. I see that I have 2 carbons, so I can translate this to 1. The moment you put the pen down, count it as 1, 2, and then we'll have an OH, but still we want to maintain that zigzag shape. In this one, you have to show the lone pair. These are the common way we draw things in organic chemistry. How about when we have a ring? So let's say we have a ring that's a CH2, a CH2, a CH2, a CH2, a CH2, a CH2 connected to a CH2. So the Kekule, the bond line structure, of this molecule, the bond line structure of this molecule will just be that. Not showing the hydrogens. They are there. We just know they are there because they're sitting on carbons, but implied. Let us discuss another example, but this time we are going to include double bonds. So assume you have this molecule. Obviously, the molecule has 4 carbons. This can be translated to a CH2, double bond CH, a CH, then a CH2. And this can be translated to a zigzag drawing of this manner, hiding hydrogens, implying the hydrogens. Carbon 1, carbon 2, carbon 3, carbon 4. Still a zigzag drawing of the same structure. Let us now discuss the last type of drawing of organic structures called 3D wedge-dash bond line structures. This we like to show because it shows a pictorial representation of a 3D structure. Let me just first of all use ammonia for example. Lewis would suggest that ammonia Lewis structure looks like this. with a lone pair. But we talked about valence shell electron pair repulsion theory. This lone pair takes much room and it's going to repel the bonds, and the bonds have electrons, they will repel themselves. So we expect that one hydrogen is going to be away from us, like behind your screen. So we use the dash, and one will be popping out of the screen, okay, pointing towards your nose, and the other one is going to be on the plane as the surface of your screen. The lone pair is still up there. So that will be the 3D representation, and we discussed and said that this is going to be trigonal pyramidal instead of trigonal planar, all because of valence shell electron pair repulsion theory. Okay, now let's take much closer organic molecule like methane. Again, Lewis would have thought, Lewis and Kekule would have stopped here. Lewis would stop at the electrons, 2 electrons around. Kekule will show 2 electrons to be a bond. But now we have to define this as to be tetrahedral, okay, discussed in another lecture. 2 hydrogens will be on the surface of your screen, 1 will be away behind your screen. We use a dash bond, and 1 will be pointed towards you, popping out of your screen. So again, that is 3D, and we can already give this the molecular shape called tetrahedral molecular shape or geometry. That's 3D. Okay, and we can do another one. Okay, 3D showing dash and wedges. So let me see. Let's do a chain like CH3, CH2, CH3. So for this one, 1 hydrogen will be on the plane, 1 will be at the back, 1 will be towards us. We are trying to maintain the zigzag. So for carbon number 2, 1 will be towards us, 1 will be away, another one towards us. Then we go down on carbon number 3, 1 on the plane, 1 is away, and 1 is towards us. That's the 3D geometry of propane. But like I say, we usually imply those hydrogens. I would just draw it like that. Okay, and I can show you another unique example. So let's squeeze here example 4. Let's say that I have this structure with a bromine towards me and a hydrogen away. That is also 3D. This will be on the plane, just like this bond is on the plane. I'm implying 3 hydrogens. There are 3 hydrogens here that I'm not showing. Bromine is toward me, popping out of the screen, pointing towards my nose. The hydrogen, I should not be able to see it. It's behind my monitor. It's away. Okay, that's a 3D structure. So again, remember, we use wedges, which will mean toward or up, and we use dashes, which will mean away or down. Those are the different ways we can show organic structures in organic chemistry. Just practice a lot. There are so many examples you can use. I hope that helped.